After studying this module, you shall be able to know about Introduction to Microwave Spectroscopy, differences between infrared and microwave spectroscopy, instrumentation for microwave spectroscopy, and applications of microwave spectroscopy. First, the introduction to microwave spectroscopy. Microwave spectroscopy is proving in recent years a great asset in the study of various problems in physics, chemistry, electronics, and even astronomy. Particularly, this has been found to be very useful in the determination of the structures of those molecules which do not give good results by using Raman and infrared spectroscopy. The ability to measure frequencies more precisely in the microwave region allows very accurate calculations than in the infrared visible ultraviolet region, and accuracy of the order of 0.001 to 0.005 Armstrong is possible. These spectra result from transitions between the rotational energy levels of a gaseous molecule on the absorption of radiations falling in the microwave region. These spectra are shown by molecules which possess a permanent dipole moment. Example, HCl, CO, H2O vapor, NO, etc. Homonuclear diatomic molecules such as hydrogen, chlorine, etc. and linear polyatomic molecules such as carbon dioxide, which do not possess a dipole moment, do not show microwave spectra. The microwave spectroscopy explores that part of the electromagnetic spectrum which is extending from 100 micrometer to 1 centimeter. This region of electromagnetic spectrum is designated as the microwave region. This lies between the far infrared and conventional radio frequency regions. Spectroscopic applications of microwave consist almost exclusively of absorption works rather than the emission type. In most of the cases, absorption of microwave energy represents changes of the absorbing molecule from one rotational level to another. Therefore, the microwave spectroscopy deals with the pure rotational motion of the molecules and is also known as rotational spectroscopy. The condition for observing resonance in that region is that a molecule must possess permanent dipole moment. When a molecule having dipole moment rotates, it generates an electric field which can interact with the electric component of the microwave radiation. During the interaction, energy can be absorbed or emitted, and thus the rotation of the molecule gives rise to a spectrum. If molecules are not having dipole moment, interactions are not possible, and these molecules are said to be microwave inactive. Examples of such molecules are hydrogen, chlorine, etc. On the other hand, the molecules like HCl, CH3Cl, etc. are having dipole moments, and their interaction will give rise to a spectrum. Such molecules are said to be microwave active. Generally, the microwave spectra obtained in most of the molecules are absorption spectra. Theoretical considerations reveal that the probability of microwave spectra is only about 1% of the optical absorption. Now we shall see the differences between infrared and microwave spectroscopy. The main differences between infrared and microwave spectroscopy are as: first, the absorption spectrum in the microwave region is characteristic of the absorbing molecule as a whole, whereas spectrum in the infrared region is characteristic of the functional groups present in the absorbing molecule. Second, the resolution of the lines in the microwave spectrum is very much greater than that obtained by the infrared method. Third, in microwave spectroscopy, the substance must be in the gaseous state. On the other hand, in the infrared spectrum, the substance must be in the solid, liquid or gaseous state. Fourth, in microwave spectroscopy, the spectra observed are nearly always absorption spectra. But in the infrared spectroscopy, the spectra observed may be absorption or emission spectra. Now we shall discuss about the instrumentation for microwave spectroscopy. A microwave spectrometer consists of the following essential components. First, the source and the monochromator. Reflex klystron valve is the main source of radiations in the microwave region. As the klystron valve emits radiations of a very narrow frequency range called monochromatic, it acts as its own monochromator. Furthermore, the frequency of the emitted radiation depends on the voltage that is applied to the klystron valve. As the voltage is varied over a given range, the emitted radiation can thus be made to sweep through a region of the microwave range. Klystrons are readily available from 3000 to 5000 microwaves per second and weaker signals up to 2,50,000 microwaves per second may be obtained with harmonic generators. One slight disadvantage of the klystron valve is that it radiates out very small energy, which is of the order of 30 milliwatts. However, since the energy radiated is concentrated into very narrow frequency band, a sharply tuned detector may be activated to produce a strong signal. Second important component of the instrument is the beam direction. The radiation emitted by the klystron cannot be handled with mirrors and lenses, but can be most advantageously transmitted through hollow metallic conductors of such geometry that the electric and magnetic fields can be utilized to the greatest extent. These are known as waveguides. These are hollow tubes of copper or silver of rectangular cross section inside which the radiation is confined. In order to maintain the direction of beam as well as its focusing, the waveguides may be bent or tapered. The waveguides are generally evacuated because if air is present in them, considerable absorption of the radiation will occur. The waveguides used in such a microwave spectrometer is now commonly used in the chemical research facilities. Third important component is sample and the sample space. The sample is placed in a piece of evacuated waveguide which is closed at both ends by thin mica windows. Round holes are made in the tube for evacuation purposes and for introduction of the gas under test. The pressure of the gas is adjusted to make the absorption line sharp. The sample must be in the gaseous state for studying in the microwave region. The pressure of the order of 0.01 millimeters mercury is generally required to give absorption spectrum. Many solid or liquid substances can be studied by the microwave techniques provided their vapor pressures are above the value of 0.01 millimeter of mercury. Fourth and the most important component is the detector. A quartz crystal is generally used as a detector. It is mounted on a cartridge made up of a tungsten whisker held in point contact with the crystal. In place of crystal detector, an ordinary super heterodyne radio receiver can be used provided it may be tuned to the appropriate high frequency. But a simple quartz crystal is more sensitive and easier to use. Fifth is the spectrum analyzer. It consists of an amplifier of detected energy and an indicator which may be either a cathode ray oscillography or a pen and ink recorder. The vibrations emitted by the quartz crystal produces an electric signal which is amplified and then displayed as a pattern on an oscilloscope screen or a recording on a chart by the pen and ink recorder. There is a diagrammatic sketch of one of the simplest type of microwave spectrometers. It has the following parts: klystron, sample inlet, crystal detector, a waveguide, amplifier, oscilloscope, and there is a supply of power to the klystron. Next is the working of microwave spectrometer. Monochromatic radiations of various wavelengths in the microwave region emitted by klystron valve are allowed to pass through the sample space containing the gaseous sample of the substance under investigation. Then the radiations are made to conduct along a rectangular tube called a waveguide. After this, the radiations are received by the quartz crystal detector, which is situated at the far end of the waveguide. After receiving the radiations from the waveguide, it vibrates and produces an electrical signal, which is amplified by amplifier and then displayed either as a recording on a chart or as a pattern on an oscilloscope screen. The pattern obtained on the chart or on the screen of the oscillography enables one to determine the frequency or the range of frequencies of the detected microwave transition. Given is a table of molecular data determined by microwave. In the molecules like HCN, the bond between C and H shows the frequency of 1.06317 and the bond of CN shows frequency of 1.15535. Other molecule ClCN, bond of C and Cl shows a frequency of 1.629 and Cn shows 1.163. BrCN, bond CBr shows a frequency of 1.790 and Cn shows 1.159. And similarly, the various data has been provided for other molecules. The microwave spectrometer described above is usually used for the measurements of the highest accuracy because the absorption lines are narrow and fairly faithful in shape and relative intensities. The use of oscilloscope poses a serious problem that the amplifier bandwidth cannot be narrowed to remove noise and thus the sensitivity is not exceptionally high. At the same time, the new lines for unknown substances cannot be obtained very easily unless their frequencies are known within the narrow limits. By changing the frequency of the oscillator and observing the intensity of the transmitted beam, moment of inertia and internuclear distances up to plus minus 0.002 Armstrong can be calculated. Data obtained for bond lengths and bond angles calculated for linear molecules and symmetrical top molecules by microwave spectroscopy are given in the tables 1 and 2. The second table shows the bond angles for some molecules. The molecule given is CHCl3. The bond angle between Cl, C and Cl is of 110 degrees and 24 minutes. Similarly, for CH3Cl, the bond angle of HCH is 108 degrees, and for CH3F, the angle is 110 degrees. Now, we shall see the applications of microwave spectroscopy. First is structural determinations. From microwave studies, one can obtain information regarding molecular symmetry and molecular parameters. This can be illustrated by considering the following examples. Structure of xenon oxyfluoride molecule. The microwave spectrum of this molecule is a characteristic of a symmetric top and is consistent with the C4V symmetry of the molecule. For the determination of the structures of OCS molecules, it was at one time thought that the compound with the stoichiometric composition FNS should have the structure SN and F. Microwave spectroscopic experiments, however, provide evidence for a nonlinear molecule with the atomic order NSF and an angle of 117 degrees. One of the most noteworthy studies in the field of structural organic chemistry was the exact determination of the geometry of benzonitrile. It is interesting to note the deformation of the benzene ring from the regular hexagonal structure. The inversion spectrum of ammonia. It was the first molecule to be studied by microwave spectroscopy by Bline and by Tons. In the spectrum of ammonia molecule, each of the lines is split into a double due to the inversion of the molecule. Measurement of barrier heights. Microwave spectroscopy can be used in measuring the barrier heights of certain molecules. If a part of a molecule can rotate about a single bond, the internal potential energy of the molecule will depend on the orientation of this part with the rest of the molecule. The structure of ozone molecule. Microwave spectroscopy is successful to deduce the correct triangular structure of the simple ozone molecule. Previously, its correct structure could not be established by optical spectroscopy and electron diffraction technique. The abundance of isotopes. The microwave spectroscopy is successful in determining the isotope abundance because each molecule possesses a unique moment of inertia depending upon the particular nuclei present. An interesting example of quantitative chemical analysis was reported by Southern et al., who in determining isotopic abundances were able to determine nitrogen 15 in the range of 0.38 to 4.5% within plus minus 3% and carbon 13 in the range of 1.1 to 10% within plus minus 2%. Only 0.00015 mole of gas was required for the determination and procedure only took 10 to 15 minutes per sample in the case of microwave spectroscopy. Microwave spectroscopy is proving in recent years a great asset in the study of various problems in physics, chemistry, electronics and even anatomy. Microwave spectroscopy has been found to be very useful in the determination of the structures of those molecules which do not give good results by using Raman and infrared spectroscopy. The microwave spectroscopy explores the part of the electromagnetic spectrum which is extending from 100 micrometers to 1 centimeter. The absorption spectrum in the microwave region is characteristic of the absorbing molecule as a whole, whereas spectrum in the infrared region is characteristic of the functional groups present in the absorbing molecule. Microwave spectrum shows better resolution of the lines than infrared method and many more. The instrumentation for microwave spectroscopy consists of the following essential components. First, the source and the monochromator, the beam direction, sample and sample space, detector and the spectrum analyzer. Microwave spectroscopy is used for structural determinations that includes structure of xenon oxyfluoride molecule, structure of OCS molecule, determination of the geometry of benzoyl nitride, the inversion spectrum of ammonia, measurement of barrier height, the structure of ozone molecule, the abundance of isotopes, and the technique can also be used for quantitative chemical analysis.